Bon, okay, so continue.
Okay, so welcome everybody again for this tutorial project, where this time around we're going to talk about room acoustics in order both to test our resonators and to see also what's happening in the high frequency range with the tonal quality. So what we want to have is if we are in a studio and record some songs or mix some songs, we want to have a room that sounds as good as possible in order to do the mixing and mastering as we wish. So I've divided into a bit of theory. Then we're going to go straight into COMSOL Multiphysics and go both in pressure acoustics for low frequency range and ray acoustics for high frequency range. And then we're going to merge the two responses into something called hybrid response. And we're going to see a bunch of results, frequency spectrum, visuals as well with the ray tracing. I'm going to go more into that. So about tracking room. So in a recording studio, we can either have something called a vocal booth. So for someone that record vocals into a small cabinet. And we have the control room where we have the mixing engineer sitting and mixing the sound. Back in the days, it was a different approach. We had many more instruments into a room that is way larger. So you have an effect of electronics, the microphone you use, the processor you use, but the effect of the room is very important, as important as the mic techniques that, well, if you're closer to the mic, you get more bass. If you sing off axis, you get less sibilance. But most importantly, how big is the room, how reverberant is the room, is going to greatly affect the recording. So that's why in a recording situation or mixing situation, it's important to tweak the room and its frequency response. So as I said before, we're going to divide the study into two different aspects. With the low frequency, where the sound wave radiates into a nice tropic shape, and the high frequency, which have much more directivity. So that's why we're going to talk about a modal analysis for bass frequencies and a diffuse reflection diffuse field for high frequencies. And in between, we have something called the Schroeder frequency, which defines the moment where we go from modal to acoustic geometry, geometric acoustics. And in between, there's a transition. And this is calculated with the reverberation time, the volume of the room. Then about the listening position. So one very important thing to consider is to be at equidistance from the speakers and from the side walls. So that's one thing to respect every time. And we have something called the first reflection. So when the speakers is emitting sound, you have the direct path, but there is also a path that we don't want, which is the specular reflecting path. So the sound wave is bouncing against the wall and arrives with our ear with a slight delay, and we don't want that. So this is how it looks like into a graph. So if I have a flat surface, I get something called comb filtering. It's because of those specular reflection. And now if I use diffusers, I see the polar pattern is way wider. So I can prevent the listener to have specular reflection. So that's something when we're going to talk about ray acoustics, which is very crucial. Now, room modes. So modes are static energy based wavefronts. So at some position of the room, at certain frequencies, I'm going to have more acoustic pressure than in others. And that's what we see in those isosurfaces. I can also see that as the reverberation time. When I have a room mode, the frequency of interest is reverberating much more than the rest. And this is discrete modes. So I can either calculate them if I have a simple geometry, like a rectangular shaped room, or I gotta compute that into a 3D model and to find all those room modes, and that's our resonators. We're gonna tweak them at those frequencies, basically, to make it simple. So the software we use is COMSOL. It's a multiphysics software where we can do magnetism, of course, mechanics, acoustics. We can do pretty much whatever we want with physics. So I talked earlier about power acoustics, and now we're going to see how do I handle that in COMSOL. So that's a visual of my room, and we're going to see a picture of that later and tell me if it looks real. So I set up 4 acoustic panels, which are porous absorbers themselves, like very simple, no resonators for the moment. So all I need to do is to declare them as a porous absorber using the Mickey-Daly-Basley model. And remember, I only need to input the flow resistivity and the thickness of the absorbent. There's also the possibility to do that with the GCL model, where I'm going to have to tell him also the tortuosity, the thermal length, etc., etc. So just to bounce back to what I was talking about earlier. And now if I want to do impedance is going to help us for the resonator this time. So I have, in my room basically, I have a set of instruments, a drum set. I have those acoustic panels, and now we want to add resonators. We don't know what frequency to tweak, so this study is going to help us to see how much absorption can I get with those resonators. So virtually, this doesn't exist yet, but I put some resonators all across the room, rear wall, side walls, even a bit under the desk. And the first model we're going to test is the RCL model, as before. So I explained it earlier. I got to input the resistance, the compliance, and the inertance. And same thing if I use a Cox and D'Antonio model with the 3 equations we have seen earlier, that I compute into a function in COMSOL. And now I call this function into the impedance setup. So I call it, the function is called alpha Cox. The sweeping parameter is the frequency or the pulsation. It's the same. So alpha Cox of AC per omega. So when I launch my study, whenever I'm at the resonant frequency, I'm going to have absorption happening on every of those walls selected at a magnitude this time around of 0.7. That was an earlier version. We saw we were about 0.35 for the resonators, but hopefully you understand the principle. And now I need a source. So the source in low frequency is the subwoofer. And the subwoofer is designed like that. We're going to use a port. It's something called a port model, where I just have to tell him the power, and eventually, if I have some phase information, I can also tell him about the phase. So that's all for the setup of pressure acoustics, low frequency, and now we shift to high frequencies with ray acoustics. So in ray acoustics, the 3 most important parameters are the receiver, so the virtual microphone, the source, and also the walls, whether they do specular reflection, if you remember, or if they are diffusive, or if they are absorptive. So the receiver, in reality, has a polar pattern, like any microphone, either cardioid or whatever. But in our case, we're simply going to go with omnidirectional. It means that it's going to pick up sound from every direction the same way, which is in reality not exact, but for a first shot, that's what we're going to use. And there's the possibility to input a directivity in logarithmic scale, and describe every angle in accordance. Now the source, we're going to first use source with directivity, which works pretty much the same way. Now I need to set up something called an SPL reference. So if I'm 1 meter away from the source, I get 90 decibel. And if I'm 2 meters away, I can calculate the loss. That's geometry, very simple acoustics. And another way to do that is to input a submodel called a lumped speaker. So a lumped speaker is an electrical circuit, analogous again, where I have the coil represented as a resistor, also an inductor. The membrane has this little mass spring system, and basically when a magnetic field is created into a coil, it's going to translate that to the membrane that moves and recreate the sound wave. That's how a speaker sounds. So you get electromagnetism, mechanics, and acoustics. That's a free physics model. So I can do that as a multiphysics modeling, but I could simply do that with an equivalent circuit. So it's more user-friendly. And then to calculate the SPO, I do something called exterior field calculation. So I have my membrane over here, and I create a virtual curve 1 meter away, for example. And I tell him, calculate me the SPO at each of those points, and we get a curve like that. With the port we use, basically we have a line like that. So it simulates the sound wave as the same for each frequency, which is in reality not the case. In reality, a speaker doesn't play every frequency the same way. That's called sensitivity. And then I need to tell him about the walls, if I want them either reflective or absorptive. And what we're going to use is a mix of diffusion and reflection with this set of equations. It comes from Vorlander and I don't remember his name, where we have a part which is specularly reflected and one part is scattered, so it's diffused. And all I need to do is input the coefficient, which I interpolate into a function. And if I, let's say, 1,000 hertz, I have 0.2 absorption coefficient, then it's going to calculate the rays in accordance. So in ray acoustics, we are using rays, which are vectors. So if a ray to strike a wall, if it's purely specularly reflected, it's going to bounce back with the same angle. Now, if I had a little bit of diffusion, it means that a part of it will be specularly reflected, but a part of it is also going to be diffused. And that's what the mixed diffuse and specular has. Now, we're using plaster walls, so plaster walls usually is only specular, but if we pay attention to the roughness, the surface, there's necessarily a little bit of diffuseness as well. And now the results. So one thing when we compute ray acoustics, which is very interesting to look at, is the ray trajectories throughout these little balls that scatters and bounce back. And we can see over here the first reflection points. So if there's any absorbent to install, then that's probably going to be on the surfaces that see the rays strike over here, for example. So that's one way to approach it. And now I can also look at the impulse response, which is a time domain. We're in a time domain study. And the peaks we can see over here is the peaks from the specular reflection again. And we want to erase that. And now if I look at some quality factors from room acoustics, I have, you can see the reverberation time is erroneous from this is extracting from measurements I made. I'm going to show you later on the setup I use for that. So reverberation time, as of now, as the progress went, we are way out of there's a big error, let's say. But now when it comes to the clarity and those other factors, we see that we close it. So this needs to investigate more and to go deeper into the settings to match the measurements from the model. And now the impulse response. So we're in the time domain with wave acoustics. But what I like to look at is a frequency domain graph. So for that, I'm using something called a discrete Fourier transform that takes the impulse response in time domain and show me the equivalent in the frequency domain. So I can see that the dips and the alleys and values I see is due to the specular reflection effect. And when setting up that thing, I can set up a range, set up some smoothing, tell him about the scaling also. So for the measurements, I used a little mixer, barrier mixer, a measurement microphone, which is entry level, and that's the room I modeled before. So at the end, you tell me if I modeled it well. So those are the absorbers I set up, and of course it misses the resonators. They are waiting to be built over there, but I need those results to build them basically. So the measurements were done using the Room EQ Wizard software, and that's the first simulation I made. And you see that it's pretty close. The peaks are very near, and we get the same kind of shape. So it was convincing at first glance. Now I've interpolated a result, put that in the same graph, and that's the measurement versus reality in the low frequency range. We're in pressure acoustics. So we see that some peaks are fairly represented. Now there is some error down 75 hertz, but over there, all the way up to 200 hertz, it's pretty satisfying. Now, I also did a comparative study with the room without the resonators and with the resonators. I tweaked the resonators at 72 hertz using the Cox and D'Antonio model. So at 72 hertz, when I don't have the resonators, I'm over there with 105 decibels. And when I put those, there was 92 resonators, I have 85 decibels. So I have more or less a 20 dB loss with the resonators. So it works. But do I need as much absorption? Do I really need to put 92 resonators in my room to get that just for one mode, by the way? So we're going to discuss that later. And then I can do a comparative study also. So with the RCL model, the circuit, and the Cox and D'Antonio model. So we saw that the frequency, there was a mismatch. I had 72 hertz before for the RCL model and 52 for the Cox and D'Antonio. But thus, the absorption, the global absorption at the end of the day is pretty similar. So I can use the RCL model to model the resonators, even though the frequency is not that close, because the result in the room is very similar. And now I can see the effect of parameters with the length, but I'm going to go over there. That's the first mode, the model distribution, and the model distribution doesn't change, basically. And now I have the hybrid response, which is the combination of those two. I put some filters. I have the pressure acoustic response, ray acoustic response, and I want to combine them, and that's how it looks like. And so, finally, for the conclusion, we did successfully create a full range from 20 to 20,000 hertz room model to model what's going on with sound waves and the sources and everything we wanted. Integrate the resonators and compare the models, and also add a say on the reflection of surfaces. And now for improvement, especially in way acoustics, we would need to include a lumped speaker boundary, as I said. In way acoustics, it would be from external calculation field. We can do that directly, and eventually have filters if we want to create some more realistic speakers. Right. So thank you for listening.